Okay, the time has come to design our switch mode power supply, and I want to start it straight off here, right at the whiteboard. So this is the circuit that I plan on using, the topology anyway. You can see I haven't really filled in any of the values because we're going to need to go to the data sheet for the MC34063A and figure out how to do that. I actually chose this particular controller because it has a relatively high voltage. It's a pretty fairly common chip, and it's used a lot for Nixie tube power supplies. I know that it's going to be stable at that 200 volt output range because we're taking 12 volts and going all the way up to 200 volts. The bigger the difference between your input and your output voltage on a boost converter, the less stable overall it's going to tend to be. Not only that, but boost converters in general are already pretty unstable compared to a buck converter or a forward or some of the other topologies. And that's because the inductor is storing the energy and you're switching into high frequency, and that energy that gets stored in the inductor, once the switch turns off, it goes to the diode and stores it in the capacitor there. It's difficult to get that high frequency characteristic working pretty well. So in order to test this, I'm going to put it on my breadboard, but I want to run it at a relatively low frequency. So I'm going to set it for, say, around 30 kilohertz or so, because if we go up to hundreds of kilohertz or megahertz or even tens of megahertz that some of these chips can go up to, it's just not going to work on the breadboard. You know, it's going to be difficult enough trying to get this stable on the breadboard. We don't need to make it worse by making it megahertz range. So what I want to do is go ahead and start going through some of the calculations so we can fill in some of these values. Alright, before I get too involved in giving some preliminary values, let me just talk about how this circuit works a little bit, because it may not be readily obvious right away. Anyway, this particular chip here, it is supposed to be a kind of system on chip for switch mode controllers. Everything that you need, including the output switching transistor, is all built into this one chip. So all you need is, say, a timing capacitor here, voltage divider for setting the output voltage that you want, a current shunt resistor, a inductor, diode, and an output capacitor, and you have an entire switch mode circuit. So if this has the transistor built in, why do we have one here? Anyway, the reason that we have one here is because this is made for up to about 40 volts DC. Well, obviously we want 200 volts. So in order to get to the 200 volts that we want, we need the external transistor that can handle the higher voltage without, you know, going poof. Okay, so we have a input capacitor here. This basically is your charge capacitor, storing charge locally from your 12 volt supply. So this is your input capacitor. It goes here to power the chip. Then it goes up through this resistor here, which is a shunt resistor. This, through pin 7, monitors the current, the peak current that's being pulled out through your switching circuit. And that helps control that. Then we have another current limiting resistor here on pin 8. Pin 8 is actually connected internally to the internal version of the transistor that we have here. So this limits the current going to that transistor just as a protection mechanism. So we'll pick probably a standard datasheet value for that, and I'll go ahead and, well, don't have my marker. Okay, let's go ahead and fill that in. 180 ohms, straight from the datasheet. Okay, and then we continue on here, and it connects to pin 1. Also connected, I believe that's the collector of the internal transistor, so that's, again, just connected to power there. We have our inductor. Like I said, this stores the main charge, which will ultimately create our 200 volts, so to speak. Down here, pin 4 is ground. Pin 3 is our timing capacitor, so that sets up the typical pulse timing of our PWM. Here's our output here on pin 2 from that transistor internally. So this is just kind of an extension of that. The internal transistor is turning on the external transistor. And this is just a pull-down resistor for the gate of that MOSFET there. And we're going to select kind of an arbitrary value for that. I'm going to go with 330 ohms. If it ends up not working well, we can always go ahead and change that. And we have our output transistor, a freewheeling diode, just like you would have in any switch mode supply. I'll explain that a little bit more later. And an output capacitor that stores our 200 volt charge out. And then, of course, down here you have a voltage divider, which I've added a potentiometer to kind of adjust the voltage to where we want it. And you can see that gets feedback from our output back to our chip, and so we have a loop here. In fact, we have a few loops. We have an input loop here, which is high current switching, and that gets switched high current through here, up, around, through our inductor, down to ground through our MOSFET. And then when the MOSFET gets turned off, we still have a magnetic field inside here. Our inductor has been fluxed. And if you know anything about inductors, they don't like to be turned off really quickly. They have a magnetic field around them that's collapsing, that induces EMF, a voltage, that wants to go somewhere. Well, it can't really go that way. There's nowhere for it to go. So what happens? Well, it goes in the opposite direction it was charged from. So during charging, that was positive and that was negative, right? Because here's your positive coming in. That's negative going out. Well, what happens is it reverses like so. And you have this is conventional current flow. Don't get me started on electron versus conventional because I don't like it. And what we'll have is a current coming down here. Well, it can't go through our transistor that's switched off. So where does it go? Out through our diode, through our capacitor, and then back up through ground through our circuit. And before that can even finish collapsing its magnetic field, what'll happen is our transistor will turn back on again. It'll draw power back in through that, and it will turn off again, do the same process. But our capacitor hasn't had time yet to fully discharge from where it was. So what does it do? Let's say we had our 12 volts on it from the first time. Well, now, because it didn't have time to discharge yet, it added another 12 volts to it, which made 24. And then our system happens again, we get 36, and so on until you get your 200 volts. It's going to continue until your feedback resistor, which comes off over here, off of your output, sees that 200 volts that it's looking for. Then it's going to start telling this transistor, all right, start controlling the PWM, because we don't want to be just continuing to come up in voltage. Let's scale that back and try to keep that output at 200 volts. So it'll PWM to this transistor as needed to keep that capacitor at the output voltage that you want. So you can see we've got several loops here. There are relatively high frequency, 30 kilohertz. Well, for a breadboard anyway, 30 kilohertz can be pretty high frequency. 30 kilohertz is kind of what I chose. This particular chip I think goes to 32 kilohertz, so it's near the maximum. And what I wanted to do, my real design goal for this was to get it above 20 kilohertz, get it above the audible range of human beings, because 20 kilohertz is often referred to as the upper hearing range for a good human ear. Me, I doubt I can hear 20 kilohertz, but 30 kilohertz, that should be high enough up there that shouldn't be a problem. There'll be the odd harmonics, capacitors and inductors can resonate at that frequency, and subharmonic frequencies that can be audible, but hopefully it's attenuated enough that it doesn't cause a major issue. Okay, I've ranted on enough about how this works. I say we go to the datasheet, we go through. We're going to go look at the formulas on the datasheet that admittedly looks quite daunting at first blush. But we're going to go through one formula at a time, and we're going to start to calculate some of these unknown values, like the shunt resistor. We're going to calculate the voltage divider down here, our timing capacitor, the size of the inductor, the value of the inductor rather, that we should need. And from there, I think we can start to make some decisions about what kind of diode we want to use, what size we want our input, or rather output and input capacitors to be, and so forth. So let's get to it. Alright, so here are the formulas that we need to use to calculate the various components in our power supply. Yeah, admittedly it looks quite complicated. Look at all that stuff. But honestly, it's not nearly as bad as it looks. Yeah, it's a little bit cluttered on the paper, but you can see to the left here we have our various things that we need to compute. We've got the time on to time off, time on plus time off, time on, timing capacitor, peak switching current, the resistor, the shunt resistor, the inductor size, and there's some more stuff down here that I haven't gotten to yet. So we'll go through and we'll compute these things one by one. You'll find that each item relies on the previous item being calculated in order to continue. So that's why these were done in a specific order. But you'll find that's the order that is in the data sheet. So no problems there. Okay, so let's get started on the time on over time off. This is the ratio of the amount of time that your switching transistor spends being on to being off. You can see it is the output voltage, which we know is 200 volts, is what we want, plus the forward voltage drop on our diode. I used 0.7 when I did this calculation. In reality, it's closer to 1. However, because we have this huge term up here, this 200 volts, you know, it washes out. It really doesn't matter. So we're fine with using the 0.7. Ideally, what you would want to do is, sorry, I should have had this ready. Ideally, what you would want to do is come over to your diode data sheet, and you would want to look at the section here that says instantaneous forward voltage, and you'll see that we have the UF5404 is the device that I selected, so it's this upper curve here. And we have a graph that is instantaneous forward voltage on the x-axis and instantaneous forward current and amps on the y-axis. Now, we haven't gotten there yet, so we wouldn't know. You would have to guess at what your inductor current would be or what your switching current would be. Now, we could probably make a pretty educated guess about 1 amp. As it turns out, it's actually 1.5. But as you can see from the graph, you know, it's a logarithmic scale. So the difference between 1 and 1.5, not a significant difference. So you could easily say that's about 0.8 volts, which isn't terribly far off from what I calculated at 0.7. So yeah, you know, we're in the ballpark there. So no problems at all. Anyway, let's get back to our calculation here. If I can zoom back out and see it. Okay. So we've got our 200 volts output plus our diode forward drop minus, that's Vn minimum. Now, normally you would want to say, what is the lowest voltage that you would expect to drop to? You know, we want 12 volts nominal, not 12 volts minimum. However, this is going to be coming from a wall wart plug pack, which is unregulated generally, and it tends to run at a high voltage when it's not fully under load. So I would expect that our minimum voltage would be about 12, and nominally we're probably more like 12.5 or something like that. So I just went ahead and put 12. Again, it kind of washes out with that big 200 number there, but yeah, if you were going with any other number other than 200, something lower, say for instance, you'd want to be a lot more careful about your diode drop and what your minimum voltage is. And speaking of diode drops, that 0.7, you'll notice that we used a type of diode here that is called a soft recovery ultra-fast plastic rectifier. Generally, in a boost converter of this type, what you would want to use is called a Schottky diode. It's a very fast diode, in fact, even faster than this ultra-fast plastic rectifier. Ideally, a Schottky rectifier has 0 recovery time. Now, obviously, there's no such thing as ideal in electronics, but you get nano, even picosecond recovery times with Schottky diodes. So, if Schottky diodes are so great... the other thing I wanted to mention is typically Schottky diodes have a forward voltage drop anywhere from about 0.2 to about 0.4, 0.5 volts. So it's a lower forward voltage drop. So less voltage drops equals less dissipated heat and waste. So if these Schottkys are so great, why haven't I used it in my design? Well, unfortunately, one bad part about Schottkys is they aren't super great at higher voltages. So in our design, where we have 200 volts, Schottkys really aren't ideally suited to that. It'll work. It would work, but unfortunately, they're rather expensive. You can get them in the 200 volt range, but in this instance, the better solution is the soft recovery ultra fast rectifier, because we don't really care about forward voltage drop because it's tiny compared to the output voltage that we have, and there really isn't too much of a conduction loss there across the diode anyway with the peak current that we're reaching. So not really worried about it. It's not a big problem in this design. For yours, it might be. If you're doing a lower voltage, I highly recommend a Schottky diode. So keep that in mind. So I'll move on. Sorry, I got stuck on that. Vin minimum, again, minus your Vsat, which is the voltage saturation for your transistor. And if you'll remember, we're not actually using the transistor that's internal to the MC34063. Instead, because of these higher voltages and higher currents that we expect to switch, we had to use that external MOSFET. So the number that we want to use here for voltage saturation is not the VSAT that you'll find in the datasheet for the MC34063. You'll want to use the saturation voltage from the datasheet in your external MOSFET. So keep that in mind as well. Okay, so we got that calculated. It comes out to, well, I used way more decimal places than I need to. We'll just call it about 23.58. All right, now we move on to T on plus T off. No, that isn't T on plus T off. It's one term. It's all in one. It's saying this is what T on plus T off is going to equal, which is 1 over F, which is our switching frequency that we chose. Like I said, I want to use about 30 kilohertz, so that's here. So 1 over 30 kilohertz is 3.33 times 10 to the minus 5, otherwise known as 33 microseconds. So T on plus T off, 33 microseconds. T off is T on plus T off. Again, that's this whole term here, which is our 33 microseconds up here. And then T on divided by T off, which is this whole term up here, which is our 23.58. So that's down here. Plus 1, that little itty bitty one, comes out to be 1.35 times 10 to the 6th. And again, that's basically 1.35 microseconds. Time on is our time on plus time off term again, minus T off, which we just calculated up here, is our 33 microseconds minus 1.35 microseconds equals 31.97 microseconds. Okay, so obviously these things are going to happen relatively quickly. Timing capacitor is just a standard term here, 4 times 10 to the minus 5th times T on. So we take that number they give us, 4 times 10 to the minus 5th, times T on, which we calculated at 3.2 microseconds, equals 1.279 times 10 to the minus 9 farads, which comes out to be about 1,279 picofarads. It's kind of an odd value, so
we'll probably choose something in the order of maybe 1200 picofarads, something that's a little bit more typical, easy to get. All right, so we move on. We have our peak current. That's the switching current that's going to be running through our external transistor. It's going to be running through our inductor, and it'll also be running through our diode. So this is an important figure here. We want to know what that peak current is going to be, because a lot of our components are going to be designed around this figure. So what is it? Well, it's 2 times the maximum current we expect to have out. In this instance, it's only 30 milliamps that we want to use for our driving our Nixie tubes. So overall, the output current is not huge. It's quite small. So that doesn't add a significant portion to the overall figure. However, when you multiply it times T on over T off plus 1, you get a much larger number. So you got your 2 times 30 milliamps times 23.58 plus 1 equals roughly about 1.5 amps. So that you can see that's a pretty big figure. We're going to get 30 milliamps out of this thing, but internally it's switching 1.5 amps to make that happen. So you can see that switch mode power supplies have something that's a little bit different to linear supplies. You end up having these huge current swings, and that is definitely something that you need to keep in mind when you're designing, and it's something that you need to keep in mind when you're laying out your board, because you're going to have huge amounts of EMF. You're going to have noise and instability if you don't keep those loops short and tight and give it good return paths. So remember that 1.5 amps. That's pretty huge for a 30 milliamp output. RSC, that is our shunt resistor. To calculate the shunt resistor, we want 0.3 divided by that peak switching current. So the shunt resistor is basically just monitoring that switching current, that peak current, just to limit it, to make sure it doesn't get out of control and do some damage. So it's going to be a relatively small value, which it is, 0.3 divided by 1.5 amps, which is just, I assume voltage divided by current, equals 0.2 ohms. So very small, and I think we can probably find a shunt resistor in that realm, so not an issue. And lastly, we come to probably the most important, most interesting figure, so we saved the best for last here, is the inductor. Now notice it says minimum inductor. You can actually go up higher in inductor values, and you may gain some better efficiency, and you're going to have more magnetizing current. I'm sorry, excuse me. But there's also drawbacks, because as your inductor gets larger, well, your inductor gets larger. So a larger inductor is not necessarily better. You don't want a huge inductor on your circuit board. It takes up space, it creates more noise, it dissipates heat because the series resistance, DC resistance goes up. So really you want to try to stay close to that minimum, because that's going to minimize the footprint that you need for your board. Maybe we'll play with this value when we start doing some measuring and see how that affects the efficiency, see how it affects our actual performance and characteristics. But for now, let's calculate what the minimum we need is. So we take our Vin minimum, which was that 12 volts, minus the saturation voltage for our switching element, which is 4 volts, divided by the peak current that we'll see, which is 1.5 amps. We calculated up there, times time on, and we calculate that out, and we get 1.705 times 10 to the minus fourth, which otherwise is known as roughly 170 microhenries. I doubt we'll find 170 microhenries. I think next standard normal value is 180. Remember, again, that's minimum, so we want to go up in value in order to meet that criteria, not down. So if we find 180 microhenries, I'd be happy with that. So we'll do that. And that's it. We've calculated everything we need in order to create this power supply. But I think there might be one last thing we have to do. in the feedback circuit, there's a couple resistors. It's basically a resistor voltage divider that will tell the MC34063 what your output voltage needs to be. So that voltage divider monitors your output voltage that you get, and it tells it whether or not it needs to turn that transistor on or off in order to regulate it. So it's critical. These two resistors, R2 and R1, they set your output voltage. So very critical that we get these calculated right. When you go to the data sheet, it gives you V out equals 1.25. That is the internal voltage reference inside the chip itself, the 2% reference, times 1 plus R2 over R1. Well, that doesn't really help us a lot because we know what our output voltage needs to be. We don't know what R2 or R1 is yet. So how are we going to use this? Well, this is where your algebra class came in useful for you. And if you're an engineer, this is why you have to do math, because you need to be able to rearrange this formula to solve for at least one of those resistors. So I've done that here, and we've calculated that R2 equals R1 times V out over 1.25 minus 1. And when you calculate that out, you get basically a ratio. And I found that it's about 200K to 1K, or maybe 2 meg to 10K. We'll try these different combinations and see if either one is maybe more stable than the other, because obviously with a higher resistance, there's going to be less current flowing through those. That could affect stability, but then again, with a value as low as 1K in that voltage divider, perhaps that will affect stability because there's too much current being drawn. So it's something that we're just going to have to play with and see what kind of stability we get. I'm going to throw a potentiometer in there as well, a 100K pot in series with a 100K resistor to get that 200K value, and we'll see what we can end up getting here, which one works better. I think I'll start with the 200K over 1K. Okay, so real quick, here's our final design. You can see that I added to the left, let's see, can I get my finger out there? Yeah, to the left we have the 1000 microfarad bulk input capacitor, just to take off the edge, do a little bit of filtering. This should be DC coming in, but it's nice to have that bulk capacitance close to your chip, because as I mentioned, when this transistor here starts switching, it's going to pull a lot of current up through the inductor and down to ground through that loop. So you want to have some bulk capacitance close to that chip to be able to draw that current from, so you don't have voltage drop. So you can see I added that. I put 47 microfarads here, bulk output capacitance. That is your main charge storage capacitor. It gets your 200 volts, from your inductor through your diode, and it's continually, not continually, but during the off cycles, it's charging that capacitor. Then you can see we have our voltage divider here, which is coming directly off the output. I went with, instead of putting a potentiometer like I said I was going to, I went with 220K rather, and a 1K, and that should give us about the voltage that we want out. It might be a little bit higher than 200, but it'll be pretty close. I had to not really fudge the values, but because the values I calculated weren't standard, I just moved up to the next closest value that was standard. So there's that. You can see it's a voltage divider there. One thing I'm going to point out about these voltage divider resistors, you don't want to go too high in value. You could just as easily say make this bottom one a 10K and make the top one a 2.2 meg. The problem is you're dealing with relatively low currents running through those resistors at that point. That's a lot of resistance, and when you have low currents around the kind of high currents and EMI that you see in a switching power supply, you're going to end up with noise spikes, and it's just not going to be as stable. So having a lower resistance like this increases that amount of current. Normally that'd be a bad thing, but in this case you want to have a nice strong voltage divider, a nice strong pull down, so to speak, which makes a nice stable value. So that's why I went with the values that I did. you know, I'll try the 2.2 meg and 10K and see how that works, but I don't have high hopes for that. So yeah, there you go. There's our final circuit. Let's build it up on the breadboard and see how it does.